Because we know that rays of light bend when they enter materials with a different index of refraction, and that bending depends on the angle from the normal, we can use these facts to craft devices that bend light in very specific ways. So if we want to use the refractive properties of a device or a material to bend light in a very specific way, we call those objects lenses. Now, a lens is a device that takes light and bends it. Now, we're going to look at two very simple types of lenses. The first type is a converging lens. And a converging lens takes parallel beams of light. So these are incoming parallel beams of light, and they bring them to a focal point. In that each of these rays, if you had a little laser beam passing through, would all meet at the same position as capital F, this focal point. That focal point will be some distance, small f, focal length away from the lens. Now this is called a converging lens because parallel beams of light converge to a point. A simple example of this would be a magnifying glass. If you've ever played with a magnifying glass as a kid, or you can do it now, grab a magnifying glass, take it out on a sunny day, and use the magnifying glass to take the rays of light coming from the sun, focus it down on a piece of paper to a point. Depending on how intense the sun is that day and how big your magnifying glass is, the sun's rays will be concentrated to a point. All that energy will exist at a point, which can cause the paper to start on fire. So it's a way of starting fires outside if you don't have matches. If you have a magnifying glass, you can use the rays from the sun, again, depending on how intense the sunlight is. It doesn't really work well on cloudy days, to create a very small point of light where all the sun's rays converge, heating that point up and creating a fire. Likewise, we can actually create what's called a diverging lens. So here we have three parallel beams of light, just like we had before, but instead of converging down to a point, this lens spreads them out. So they spread out. They're no longer parallel, but they're diverging rather than converging. Well, if you're looking over here, these rays of light all seem to emanate from the same point. So this would be the focal point of the diverging lens. Notice that the rays don't really go, the middle one does, but the other rays really don't go through that focal point. They just appear to emanate from that focal point, and that's true for a diverging lens. And then the focal length, again, is the distance of that focal point from the lens itself. So we have two simple lenses we're talking about. We're talking about a converging lens and a diverging lens. Again, same principles apply to both. The shape of the glass is chosen in such a way to either bring the light together or to spread it out. So this is called a double convex lens. So the lens looks something like this, outward. Converging lenses have that shape. Diverging lenses are thinner in the middle and fatter on the outsides. So if you wear a pair of glasses and you are nearsighted or farsighted, you can determine if you have a converging lens or a diverging lens just by feeling the thickness of the lens in the middle and toward the edges. Is your lens thicker in the middle than at the edge? Chances are it's a converging lens. Is it thicker in the edges than in the middle? Chances are it's a diverging lens. If you have astigmatism and that's why you wear corrective lenses, you won't have this effect. You need to be either farsighted or nearsighted to see this. Now, again, the point of light where rays actually cross, or they appear to cross, is called the focal point. And that focal point is some focal length away from the lens itself. So that distance, that focal length distance, will become important when we solve problems in geometric optics. If you go to a store like Walgreens or CVS, Walmart Pharmacy or Target Pharmacy or whatever pharmacy you go to, usually they have on one of the ends of the aisles sort of this rotating case of eyeglasses. And those eyeglasses are reading glasses that you can buy, and they have different focal lengths. Now, but they're not listed by the focal length, they're listed by something called diopters. And the bigger the diopter number, the stronger the focal length potentially of the lens. This is referred to as the power of the lens. So the power of the lens is just 1 over the focal length. So the smaller the focal length, the more intensely these lenses focus, the more intensely they bend the light, the more powerful the lens. So big focal lengths have low power, small focal lengths have high power, and the power has units of what are called diopters. Now focal length is a length, so SI units of meters. 1 over the focal length is 1 over meters. 1 over meters has the unit of diopters. So 10 centimeters, or 1/10 of a meter, is 10 diopters. 1 millimeter, or 100th of a meter, is 100 diopters, and so on. So when you look at those glasses at a pharmacy, you'll actually see their power measured in diopters. And then you can take them on. If you're near or farsighted, you can put those glasses on to see if they help correct your lenses. Now, most of us probably have, if we are wearing glasses or contacts, we've gotten specific ones designed where each eye is a different, prescription. But the reading glasses you get at Target or pharmacy or Walmart pharmacy, they're basically the same 2 lenses, have the same power, very cheap way of getting reading glasses rather than having specialty made glasses. So we need to talk a bit about geometric optics and the concept of ray tracing. So we talked about a ray and how a ray is basically a beam of light from some origin traveling in a straight line, and that ray can be affected by reflection or refraction. It can be bounced off an object, or it can be bent as it passes through an object with a different index of refraction. Now, we're going to be looking at ray tracing here. We're going to be setting up lens systems, converging and diverging lens systems, and we're going to see how those rays transfer through those lenses. Now, there are 2 ways of doing that. We can either do the geometric optics detailed portion, look at the ray at each interface, use Snell's law or the law of refraction to calculate what the angles are as the ray comes into a lens and as it emerges from the lens from the normal at that point, and then see how the ray progresses through. That absolutely would work, but requires a lot of math. We're going to look at instead simple thin lenses. So thin lenses are lenses that are so thin that they're still capable of refraction. They can still bend light, but they don't offer any significant dispersion in that they don't break colors up like a prism does. So these are thin lenses, and we're going to look at 2 types of thin lenses, converging thin lenses and diverging. So a converging thin lens, we're going to draw like this. A line with 2 arrowheads on either side where the arrows are pointing away, suggesting that it's fatter in the middle than at the edges. And then a diverging thin lens, which has 2 arrowheads but pointing in opposite directions, or pointing towards the middle. So converging and a diverging thin lens. Now, when dealing with thin lenses, you can actually do ray tracing fairly easily. There are a couple of rules that your book looks at, and we'll draw these out as an example in the next part of this video. But I have them listed here, so I want to read them off. These are the same rules that your book lists. So a ray entering a converging lens parallel to its axis. So again, here we'll draw a converging lens, and here we have the optical axis. So a ray coming in and striking parallel to the optical axis, let's say this is the focal point here, will go through the focal point, missed it a little bit, but we'll go through the focal point of that lens. So a parallel ray will go through the focal point of that lens. That's step 1. Step 2, a ray entering a diverging lens parallel to its axis seems to come from its focal point F. So here's a diverging optical axis, and here are the focal points on either side of a diverging lens. So if I have a parallel beam coming in, it appears that it's coming from the opposite focal length. So this is what will end up happening, right? So parallel beam will emerge as if it's coming from the focal point. That's number 2. Number 3 states a ray passing through the center of a lens does not change direction. That's true for both converging and diverging lenses, which again simply means I'm going to draw here a converging lens with the optical axis. If a ray comes in through the center of that optical axis, regardless if it's a converging or diverging lens, it passes through straight. It does not bend. That's rule number 3. Rule number 4 is if a ray enters a converging lens through its focal point, it emerges parallel to the x-axis. That is, here's a converging lens again. Here's the optical axis, and we'll draw here the focal points, F and F on either side, so distance. So if a ray comes through the focal point and strikes the converging lens, it emerges parallel to the optical axis. That's rule number 4. And rule number 5 says a diverging lens. So we'll draw a diverging lens. Optical axis, focal points. If a ray enters a diverging lens heading towards the focal point on the other side, it emerges parallel. So here a ray is coming in. It's going to want to go through that focal point, but the diverging lens forces it to go parallel. So this ray wants to go through the focal point on the opposite side, but when it interacts with the diverging lens makes it a parallel ray to the optical axis. So these are the 5 rules for ray tracing, and we're going to look at 2 examples, one with a converging lens and one with a diverging lens, to see how images are formed using these types of lenses. All right, let's look at those rules that we just stated earlier in the video. So here we have a converging lens. So I have the thin lens drawn here, I have the optical axis drawn, and I have a little arrow. I think your book shows a person, but I have a little black arrow representing an object. Now I'm going to look at the beams coming from the tip of that arrow. Where do they appear to or actually converge? That will show me where the image will end up in this simple optical system. So, a couple of rules for the converging lenses. There were 5 rules. 3 of them applied to converging lenses. First one was rays parallel to the optical axis appear to go through the focal point, shown here in blue. And I'm freehanding these so they're not perfect. One was rays through the center of the lens continue on as if they don't bend at all. And the third rule for converging lenses, or rule number 4, is shown on that list we just talked about. Rays through the focal point emerge parallel to the optical axis. So you can see that all 3 of these rays emanate from the tip of the arrow, and they all come back together over here. So we will get an object. We will get an image here of the object, but the point of the arrow would be there, so the object would be upside down and magnified. See how much bigger this arrow is than that arrow. So how do we figure out, given the object distance, d sub o, how far from the lens is the object? Where is the image, d sub I? How far away from the lens is the image, given the focal length, small f, which is the distance of the focal point from the lens? Well, to figure that out, we can ray trace, and then if we had a ruler and we did very precise measurements, we could actually measure what this distance was, measure the focal length distance, and measure the image distance. If you have really good drawing skills and you're very precise with a ruler, you can actually do this ray tracing and come up with a reasonable answer. However, there's a mathematical formula that gives you the precise answer. It's called the thin lens formula. It states 1 over the object distance, again the distance of the object from the lens, plus 1 over the image distance, the distance from the image here to the lens, is equal 1 over the focal length of the lens. That's called the thin lens formula. So if you know the focal length of the lens, how far is the focal point from the lens, and you know the object distance, you can calculate the image distance. Now note that this is 1 over dO, 1 over di, 1 over f. Right? It's not dO plus di equals f. You have to make sure you're careful with the algebra, right? Only add fractions if they have a common denominator, that sort of thing. And of course, make sure all the objects have the same units, otherwise it won't work. Now, for a diverging lens, I apply the same rules. It's a little trickier and the drawing's a bit smaller, but your book has a drawing to follow along. I have an arrow here. I have the diverging lens drawn in the black dotted optical axis, 2 focal points. So I have, for the rule number 2, a parallel beam, a beam parallel to the optical axis, emerges as if it's coming from the focal point. So that's the blue beam. The red is number 2. The red says a line going through the center of the lens proceeds on as if it's not bent at all. And the third rule for diverging lenses, which was rule number 5 in the sequence of rules we had earlier in the slide, earlier in this video, a ray that appears to go through the far focal point will emerge parallel to the optical axis. So here we have the blue ray coming up, green ray parallel, the red ray going down. But see how these 3 rays never converge, right? Unlike before, where they come together to a point in a converging lens, here they're diverging. They will never come together. Well, how do I know where the image is then? Well, our eyeball, when we look at these rays, our eyeball doesn't know that these rays have been bent at the lens. So if I draw dotted lines backwards, the blue dotted line is where the blue ray appears to come from. The green dotted line is where the green ray appears to come from. The red line is where the ray appears to come from. Since it doesn't bend, it is still straight. And you can see all of them converge at that point here. So this little tiny arrow shows you where the rays appear to converge. They don't actually converge at that point. They just appear to. So here the rays are actually converging. All 3 rays go through the exact same point. Here the rays don't go through the same point at all. They spread out, but they appear to emanate from the same point. So we get 2 different kinds of images here. When the rays actually come together, this is called a real image. You can use a projector, slide, screen, or something, place it there and actually see an image of that object. And when the rays only appear to come together, that's called a virtual image. You cannot put a slide or card there and actually project an image. A wonderful example of a virtual image is your mirror image. Look in a mirror and you see yourself, but the rays of light really don't go behind the mirror. So if you're 2 feet in front of the mirror, the image of yourself is 2 feet behind the mirror. But if you actually go out of the bathroom and dig into the wall 2 feet behind the mirror, the rays of light don't really go there. They just appear to have gone there. So how do we use this thin lens formula? Well, a couple of caveats if you want to solve these problems. The first of all, you can see diverging lenses and converging lenses behave differently, right? Converging lenses bring the parallel beams of light together. Diverging lenses bring parallel beams of light and spread them out. So the focal lengths have different signs. So if I tell you I have a converging lens with a focal length of 10 centimeters, that means the focal length is positive 10 centimeters. If I tell you I have a diverging lens with a focal length of 10 centimeters, that means the focal length is negative 10 centimeters. So if you want to use this formula properly and figure out where the images actually are, and we'll be doing that for homework problems, exam problems, and so on, you need to remember that converging lenses have a positive focal length, diverging lenses have a negative focal length. Additionally, when you solve for the image distance, you might get a positive or negative number out, depending on how this formula works. If your image distance, d sub I, is positive, it's greater than 0, it's a real image. The rays of light really converge there. If your d sub I, if your image distance is negative, it doesn't mean you made a mistake. It means that the image is virtual. The distance, so let's say your image distance is plus 5 centimeters. It just means you're 5 centimeters from the lens and the rays really converge there. It's a real image. If you end up with negative 5 centimeters, that means that the image is still 5 centimeters from the lens. It's just that the rays don't really converge there. It's a virtual image 5 centimeters from the lens. And for lenses, real images form on the opposite side from the object. So if you have the object on the left-hand side here, it's typically drawn. Real images show up on the right-hand side. Virtual images show up on the same side. So if you have the object on the left-hand side, the virtual image will also be on the left-hand side. So this is the distinction between real and virtual images using the thin lens formula. And one last thing to mention, same drawing we've had before for a converging lens system and the thin lens formula, and then again listing here the variables and what they mean. I've added here an object height and an image height. You can see that they're not the same. The object height is about 1/3 of what the image height is in this example. Well, how do I figure out what the image height is if I know what the object height is? Well, any change in height is called magnification. So if an image appears bigger than the original object, we say it's magnified, but also if the image appears smaller than the original object, we say it's been magnified. Magnification doesn't always mean bigger. It just means that the size has changed. So to calculate the magnification of a lens, it's a simple relationship between minus the image distance over the object distance. So if I know what the image distance is, and I know what the object distance is, I can calculate what the magnification of the lens is. Once I know the magnification is just the ratio of the image height over the object height. So a magnification of 2 means the image is twice as big. Magnification of 10 means the image is 10 times as big. Magnification of half means the image size is half of the object. Now again, there's a sign issue here. If the magnification is greater than 0, that tells me that the image is upright. If the magnification is less than 0, that tells me the image is inverted. So d sub I, we have to be careful. Notice there's a negative sign here, but d sub I itself can be negative, right? If it's a virtual image, d sub I will be negative. Then you'll have a negative times a negative, which will give you a positive magnification. If d sub I is positive, if it's a real image, then you'll end up with minus a positive sign, which will be negative. So for this example, it's clear to see this is a real image because the rays actually converge here, but see how it's inverted, right? This is an upright object, but the image is upside down. So the magnification I should calculate for this, if I use the values, if I gave you values here and plug them in, the magnification should be negative. So the value, positive or negative, tells you if the image is upright or inverted. And then the magnitude of the magnification, the absolute value of the magnification, tells you how much bigger or smaller the object is height-wise. So using all of these things together, you can calculate what the image distance is, what the magnification is, and what the change in height of an image is compared to its object, if I give you the focal length and the object distance for a converging or a diverging lens.